Thank you, Greg, and other organizers of the chapter for having me here. I am honored and delighted to be addressing so many people here who are of very diverse backgrounds, I think, except that they have data science in common. I am here to present in all humility a field report of my experience as a consultant and as a financier as to what exists by way of expectations and perceptions and actual work beyond the little bubble of Silicon Valley. So I bring you perceptions of your customers, of the customers of your kind of skills from the East Coast, the middle of the country, large corporations, banks, and so on. And these are folks, believe it or not, who spend most of the money to make things happen. And the story there is quite different from here. And so hopefully my message is one of help to you in looking at what needs to be learned for helping out these kinds of demand points, as well as there's good money to be made doing that. A few rules. One is that, fair warning, no equations or Python code in this presentation. Second one is that I have broken every known rule in PowerPoints. It's a really haphazard, pulled together bunch of slides. Bear with me. Some of them have a lot of dense material in it, and that the reason for that is hopefully you'll read it later on. And please feel free to ask me questions as I go along, because you lose the thread otherwise. My slides will take me at most about 30 minutes, so we have another 30 minutes that we can utilize in between for questions and answers. Now, by way of a little background that Greg didn't mention, I started out as a professor of finance at the Wharton School, where I did my PhD in quantitative finance. And subsequently, I joined McKinsey in New York as a co-head of their corporate finance practice, which was in the heady days of leverage buyouts. Most of you are probably too young to remember Mike Milken and those names. But we helped them out in valuation of leverage buyouts and so on. So we started a valuation practice. And that resulted in a book called Valuation, which I helped start, but I left the company after that. And so it's taken its own life and has gone into 6 editions and has sold 1 million copies. It's a huge tome these days, but it's a very easy read. But it's used now for MBA programs, as well as sits on the bookshelves of all CFOs. Don't know how many read them, though. And out of the 1 million copies sold, I don't know how many are McKinsey purchases. So anyway, that is a part of the background. Second thing, after I left McKinsey, I just started as an entrepreneur in Silicon Valley and created a fintech company, and which was going to be a product company. We had several software patents, but we never made it to a product company. We became a thriving software services company with presence in 8 countries, 600 people. I started from scratch, no capital from outside, but then got burnt in the dot-com bust. But we learned a lot. We did a lot of risk management software for the Philadelphia Options Exchange when it first started out, for major brokerage houses, for banks, for you name it. So we did a lot of geeky work, but that was then. After selling out the company, I decided to get out of IT and went off to Papua New Guinea. I don't know how many of you heard of it on the world map, but it's, so I managed their $4 billion national wealth fund, which was quite interesting. They wanted a guy with venture capital background as well as economic development background. The economic development part of it came from the fact that I was from India. So that was an amazing stint. When I first reached there, I didn't realize that it wasn't officially a cannibal country. There were living cannibals there. So I asked the chairman of the board, I said, why did you tell me before you gave me employment here? He said, that's not a problem. Never accept a dinner invitation from anyone. After that, I came back to the Valley. I did a lot of consulting all around Asia, Indonesia, India, and so on, mostly in education and fintech. Financed a bunch of startups. Some of them have been okay. The others have been duds. And here I have about 5 or 6 small companies, some using blockchain and Bitcoin, some using AI and NLP and so on, wealth management, insurance technology, credit scoring, and so on. I also do a fair amount of enterprise consulting and have a wide network, old enough, of very good consultants out there from the likes of BCG, McKinsey, Bain, and so on, as well as independent consultants. And so this is a result of not just my own work, but a lot of feedback from others. So I'm going to make a few kind of disjointed points. But, OK, see, I told you this is very dense. But this is a kind of synopsis of what I'm going to talk about. First of all, here in the bubble of the Valley, we chase a lot of shiny objects like deep learning and the latest in GPUs and whatnot, which is great. I love that stuff. But out there in the world of enterprise, they're very, very far behind. And there is a problem. The problem is that consulting companies have made major hype out of this, and there's no delivery. And I will get to that point. So the most important thing is that they can't seem to find the talent. And the talent that is really trained to do enterprise work. So it's not just simply somebody who can run machine learning algorithms or do some data wrangling, but it's also people with some amount of business domain experience. You can't do much data science when you don't have an objective in mind. What is the problem you're trying to solve, or what is the insight you're trying to get? And to a large extent, a lot of very technical people lack that. The other problem faced is that a huge portion, 80 to 90% of the data in enterprise is unstructured data. That's a mishmash of everything. And as we know, that's still a bugbear. I mean, we have done things in NLP and whatnot, but there's no satisfactory big answer to these questions of how to deal with unstructured data. IBM Watson has made claims that it has solved that problem, and because IBM is this enterprise company, that they will have access to these data islands within each company, and nobody can enter that business. But lo and behold, Microsoft and Google have started competing with them. They all have cognitive computing solutions now, whatever that means. The other point is that when you look at deep learning, which is kind of beginning to dominate machine learning as well as much of data science today, at least in the Valley, there are many successes, but many, many more limitations. And these limitations are very significant in the business world. They're great for recognizing pictures and sound waves, but if you go beyond that, or language translation, you go beyond that, there's nothing yet. And there's good reason why there's nothing yet, and why current algorithms are not equipped to deal with any of these problems. And again, I make a lot of generalizations, so feel free to attack me when you want to. And the final point I make is that when you deal with real business issues with data science, beyond the data visualization things that have been very useful, you have to tackle head-on things that are not just data-driven. So the mantra today, when I did my master's in computer science at Penn, the big thing in AI was expert systems. I don't know how many people still remember that. But expert systems were, drain the best minds of all they know about a particular topic, and then use predicate calculus and so on to write algorithms that will answer questions to to ordinary folks. That worked for a while, but then it went into this second AI winter. And then out of that came out this whole concept of forget rules, only data. So the data tells the story. Don't impose any rules into the creation of algorithms. And that's where we are today. And principally because there's huge amounts of data and also parallel processing computers that can help us analyze them. But unless you deal with some of the models and rules that have been built into business by the likes of dozens of Nobel laureates in economics and finance, plus other smart people, you will not be able to just let data tell you the story. You have to make your algorithms compatible with these constructs. So that's my pitch today, and I have a bunch of rather heterogeneous slides cut and pasted to get to the point. But feel free to stop me at any time and ask questions. All right. All right, so you know this. The great paucity of good AI talent here is because of these villains called Google and Facebook and all those guys that have sucked in all the top talent, either by paying them too much or by poaching professors or by acqui-hiring. You know about acqui-hiring, right? So they just buy up little companies just for the talent, not for the product. And then they integrate them. And so what is happening is that all these major Silicon Valley giants have all the talent that's out there that's really high end, and they continue to do so. So there's very little left out there. And the problem with the rest of the world beyond Silicon Valley is that the training levels are not good enough. The teachers are not there. The talent that gets employed into enterprise have very questionable capabilities, not because they're bad people, it's because of their exposure, okay? And yes, there are many training programs in the Valley. There are many more out there as well, but the quality is incredibly, it's all over the map, let's put it that way. So this basically says that, look, this is the amount of money that's gone into this. You go to LinkedIn, you'll see so many vacancies, hard to fill, high salaries, blah, blah. But this has to change. The second point I make is that, that data science is not just computer science, but it's also math and stats, probability theory particularly, and then business domain expertise. Now, that's a lot to ask from a single individual. It's hard enough to qualify as a computer scientist. And it's also a very onerous thing to go through a rigorous MBA program and then get business experience. And then a lot of computer scientists are not really well versed in probability and statistics. So the point is, how do you put all these skills together? And that's what makes it so challenging. According to Udacity, that's the slide hiding behind the other slide, other picture, the basically says that these are the kinds of skills that are required, and they are not to be found in a computer science program or an MBA program or a math stats program, but there are little bits of each in this whole thing that we need to pull in together. And I mean, if you look at the layout, look at the list of courses that are offered by the top business schools, it's a 2-year intense program just to get there. And so how do you expect people to blend all this into their young lives and go out there and be super consultants? That's a huge challenge. All right, so what we have today are that people like Andrew Ang and others have created amazing video classrooms, video lectures, and Coursera has done some tremendous work. Udacity, of course, everybody's aware of. But, and also, if you want to do a very minimal business quote-unquote MBA program, you can do it for nothing at Harvard. So there are these things available. It's all out there. So what you have to do if you're really enterprising is to train yourselves in these things. But that's not easy either. And I find that a lot of people who are not that motivated or not that disciplined will never be able to use purely online programs to learn. And hence, I've noticed that this whole model of blended learning, and there are many models, created by the likes of Clayton Christensen and others, have become very useful. Now, they've become very useful in the K-12 context, but now they're being used in the learning of data science. And Udacity Connect, which started just a few days ago in the Valley, is one example of that. They've realized that pure online doesn't work. Because pure online is one part of it. You have to collaborate. You have to sit and do hands-on software work or data extraction work or whatever, and have peer reviews, peer discussions, as well as people with superior knowledge to come and help you out. So they've started this. In New York City, believe it or not, they've started something that's, I think, is even more useful, which is training data analysts. So one of the skills that are in immense demand, but with zero supply almost, is good data analysts, people who are trained in data wrangling, in data visualization, and have the ability to operate in an enterprise setting. So see, these enterprises have this massive data, right? Actually, I'll come to that later. There's a slide on that. Any questions so far? So are the data analysts not there, or they're not there at the low price that people think that they should be paid? Now, interesting question, because what I see a lot of is very high-paid machine learning consultants, $200, $300 an hour. They do the data prep work, okay? And on a typical enterprise assignment, 80% of the work is on the data wrangling part. So for them, it's a great bonanza. I mean, but the fact of the matter is that by the time the bills are paid, the enterprise client is asking, I spent all this money, what have you done? All right. Now, also, a lot of these algorithmic geniuses don't like doing data wrangling. So what they do is they do a half-baked job. And within an enterprise, data wrangling is a very different story than just data prep as we know it here. I'll come to that a little bit later. But when I looked around to see what's available to train people, I came across this company, Trifacta, which I'm sure many of you have heard of. And Trifacta was created by Berkeley professors as well as some ex-Google people, and now is offered through Google. So Google Cloud Data Platform, GCP as it's called, which changes by the minute because their offerings are so dynamic that anytime you call them, it looks different. But what they've done now is quite interesting. So they have a whole data prep offering on the cloud, which is essentially the entire Trifacta data wrangling software. And then they have embedded data visualization in there. So you don't have to buy Tableau and a data robot and things like that. They're all in there. And so you pay by the instance of use. You don't pay for licenses. So that becomes quite interesting for at least training purposes. And so the interesting kind of output from this training exercise is great data visualization on the fly. So you go around the enterprise looking at all the end users and show them, this is what a dashboard will look like. This is what the questions that you can answer. Tell me what else I can do to make it your baby. And they will tell you that. And if they see that, you get a buy-in that you can't get through presenting PowerPoints. Now, the other thing that I don't know how many people in Silicon Valley pay attention to, we have all these buzzwords in the IT world, but the current one in data is data lakes. Anybody not heard of it? Okay, so we had these data warehouses in the past, right? ETL. And so what has happened is that the thinking now is, let's not deal only with structured data. Let's take everything that you've got. And unstructured data is huge. So we will put that in. And we will put it in a raw format in so-called lakes. Okay? And then we will not kill the old data warehouses. They'll also coexist. But by the time you've done ETL to the old data warehouses, the raw data is kind of mangled. You can't get back to it. So the data lakes have this concept that the raw data is in there. And it hasn't changed because you played around with it. But when you have played around with it, the results are also there. So now you have this coexistence of cleaned up data, analyzed data, raw data, and so this new approach is that you use tools, and this whole data across the enterprise, which is an enterprise data lake, you take your concept of data wrangling to each of the end users. And each of the end users will then say, I need this and this and this. I need supply chain optimization data, and I need to get it from all sources, from messaging to emails to external data to all kinds of things, shipping information. And so you're able to pull that out of the lake and run dashboards and show it to them, at least as a beginning exercise. Now, let's move on to algorithms. So these fancy charts are what I see my colleagues in McKinsey and BCG and Bain and other places presenting to their clients. So this is a CXO presentation where they'll say, hey, these are the industries that are really going to benefit. These are the departments that are going to benefit. Where did you get the information? Oh, by just polling people like you in other companies. Okay, that's wonderful. But at the end of the day, how do we know that, number one? How do we get behind this? And, please don't, I mean, so far, I've seen this whole business as you go in, you claim that you know a lot about the domain that the business is in. You tell them about what everybody else does in that domain because you have clients in that business. You don't name names. And then you look at all the data that you can get a hold of. And McKinsey and Bain and all these people are really data-driven consultancies. They have espoused data-driven decision-making before anybody else that I can remember. But what they do is there's data in the small. There's data inside the company. The data outside the company, it's from past gigs with other companies. So they combine all of that, and what's the output? So a typical project would be 3 months, about $3 million, and it's be a PowerPoint this thick, all right? And so now that these companies are pushing the hype on this machine learning to the point where the customers are saying, I'm not going to give you $3 million for a PowerPoint. I want to see actual programs in place. I want to see code written. I want to see the effect that the code has on the valuation of the company. Does it change our decision-making markedly? Does it give us better pricing power? And so on. And these companies are now, these consulting companies, are now scrambling to find data science talent everywhere in the world where they are. Most of them are in 100 countries. So they've been hiring willy-nilly, places like India and China, thousands and thousands of data scientists. And then they're finding that these people have no concept of enterprise consulting. So now they're training them. So it's a very frustrating experience for them, from what I can gather up to the minute. So they also are facing the same talent crunch that the end user enterprises are facing. One example of a real success story on the enterprise side beyond the internet companies is GE. You heard of GE's successes. GE has created this software entity, mostly in the Valley, where they have exciting projects. So they've been able to hire thousands and thousands of good data science and software engineers. And what they have been embarking on and actually completing a number of projects on is what they call digital twins. How many people have heard of this? Yeah, so not a lot of people. So let me tell you a little bit about what they are. So GE is in the business of selling very large, complex machinery, whether they are power generation or medical instruments or MRI machines, all kinds of things. And when they need repair, it's a very expensive proposition to do it manually. So they now have a complete version of it, which is in software, in their headquarters. So every individual machine has a twin in software. And they are connected by internet. So they can run non-intrusive, in physical terms, repairs that way. They can upgrade software, just like Tesla can upgrade the software of their cars without having the cars come into the garage. And so they are doing similar things. And it's been remarkably successful thus far, I'm told. And so, there are exceptions to the rule, but then not everybody is GE, particularly if you look at the banks. Now, the banks spend the most money on IT, and they have spent the most money on decision sciences, particularly AI. And they have really not gotten much out of it. And part of the reason is the objectives are unknown. What are they really looking for? They think that if they do AI, they'll get better decision making, but in what sense? They have to really explicate what they're looking for, and then have the data scientists come in and do their work. And that's been a big challenge as well. All right, so regarding unstructured data, and that's a really, really big issue in enterprise. And we don't think much about it here, but the fact is that this is the part of their data lakes that's growing exponentially. So if you look at that blue piece up there, that's the growth rate of, or the growth expected of unstructured data. And unless there's a solution that combines unstructured with the regular structured data, you won't get much out of it. And that's kind of where the IBM Watson philosophy started with. So the idea was that, hey, we will do this cognitive computing, which looks to me, very few people know what's inside it, but which looks to me like a natural language based search capability, where you fed computers with as much information in the world that you can, and then do searches. And there have been questions as to whether that search engine will ultimately compete with Google. But the fact of the matter is that this data is internal to these companies, and they're not going to have you share that with other people. And so they will remain islands over periods of time. And the fact of the matter is that IBM thinks that being a corporate IT company forever and ever, they will be the kings of this world, where they will come into each and every company, bring in the expertise and experience from their other company consulting, and do this for each of these islands. Nobody else will have access to it. But hasn't worked out very well. They started it in the healthcare business. A lot of money spent on both sides, IBM as well as the healthcare companies, and there's very little to show for it. Anybody have any experience in this field? The IBM Watson experience in healthcare? Sorry, yeah? Tell me. So that's one major thing. So the data, getting the data out was the big challenge, okay? And that is always a big challenge. No, data out of the entity, the healthcare entity. And yes?
Yeah, so what I've heard is that part of that problem is that the doctors take lousy notes.
Repeat the comment for the video recording.
Doctors take lousy notes. Yeah, I don't know. I mean, the doctors I go to take good notes these days, but and they send you a copy. Right now with EMR and all of that, you get your visit minutes and so on. So I think part of the problem is that people don't want to share information, and part of the is that in healthcare, there's never been a move to integrate information. Everybody is held on to their own little turfs, and they've claimed privacy, HIPAA, and all of that sort of stuff. It was yeah. Right, so he's saying that he's in the heart monitoring technology business, and why does IBM have to get into such difficult areas to get the data? It's obvious. IBM thinks that they're the kings of unstructured data. All right, so what they've done is they've fed their Watson, whatever that is, it's a bunch of computers, I guess, with every medical, a source of medical information that they could lay their hands on, private, public, whatever. And they think that the search capability will be enhanced at each and every context, but that has proven to be a real challenge for the reasons mentioned, availability, but also they found that these NLP-based, and they have a range of NLP variants that they use for this purpose. And I'm told by many of the customers that the results are very erroneous. It's full of errors. And a search produces ridiculous results. And so this whole thing will take longer and longer. People are losing patience. The hospitals have spent hundreds of millions of dollars. They want to see results. And so this thing is headed towards a bit of a disaster. All right, so yes, healthcare is probably the toughest place to go to, but that's where the money is being spent. That's where there's a lot of unstructured data. So that was IBM's wisdom. Now, what Google and Microsoft seem to be offering very recently are similar things, but they claim that with machine learning and deep learning in traditional ways, not in the ways that IBM implements it, has given them more capability to do better unstructured data manipulation. Remains to be seen, but they are offering these services. Facebook kind of has its own parameters for posting information. So they structure it themselves, right? What they're trying to do is give you richer multimedia experience. And I think this whole obsession with AR, VR is a bit misplaced and will not be that commercially successful, but then that's one opinion. But the fact of the matter is that Facebook is very internal. They're just looking at what they need for their very highly parameterized information blocks, right? But when you're in a business of search or when you're in the business of much more general things, then it becomes a much bigger problem. Okay, so the question is that comparing Watson with the other standards like those espoused by Google and so on, are rules, I mean, how do you bake in rules into a purely data mining philosophy, okay? And that's what I'm coming to at the end, but I'm going to do it only for business. Now, it's a bit of an anathema here to say that let's mix rules with data, because I think the high priests of deep learning will tell you that it's data, data, data. You do not sort of intrude the data with your knowledge or biases, okay? Let the machine figure out from the data. That can be both dangerous and highly misleading in context beyond recognition of pictures, of voice, of things that are very, very tightly contained. And in this age of big data, when you have so much data, it's not a question of randomizing this data, it's not a question of statistics, it's a question of the whole population. So you say that, okay, there are 30 billion images in the world, I have access to all of them, so what's the need for any statistical analysis or anything of that sort? I mean, I can predict absolutely what a picture looks like by training the machine over and over and over again. But that is fine. But when you come to contexts where uncertainty is what it's all about, business is about risk taking, business is about uncertainty. And when you bring in this kind of thinking, which is completely without any idea of sampling risk, randomization, and so on, you just fail. Let me get to that. So I'm sorry about this one, okay? This is kind of a whole rigmarole that I put together from my favorite, one of my favorite authors in the subject. But read it when you have a chance to do so. François Chollet, he's the creator of Keras at Google, a brilliant guy. He's coming up with a book, much awaited, called Machine Learning with Python at the end of the month. And he has looked deeply into these issues. And basically, he has confirmed what we kind of know but don't want to admit, that the deep learning algorithms are very, very specific to the data set. Okay, so you have pictures, you can only do picture recognition. You really can't use those algorithms. And convolutional works very well for it, and some other algorithms. And there's been genius at work to develop amazing algorithms that do a great job, right? But give that same algorithm, after it goes through the training and everything, something else to do that's totally apart, it'll completely break. Okay, so everything that you do is very dependent on the data. Second thing is that there is no concept of reasoning or understanding here. Okay, at least not the way we humans reason. So when you have a prediction, it comes from a black box. Now that's fine when you're doing things like imaging, even up to MRI levels, even though there are problems with that. But by and large, if you do it in finance or you do it in a business situation or a policy situation, people will want to know what the black box is. But these algorithms, by their very nature, generate black boxes that are completely dense and cannot be made any, cannot be made any sense of. Now, people are trying to figure out what's in this black box and so on. Some people I know are doing, delving into these boxes for feed-forward algorithms, and they're able to show, just like neurons light up, they're able to show what happens in these boxes. Yeah, but that's not what I need. If I am using AI to peddle a product that's for investment purposes, and I claim that you'll make a ton of money without taking any risk, and I'm asked, well, how do you know? I said, my computer told me it's a black box. Now, the SEC has come up with some sort of a statement saying that you cannot sell general products with AI where there is a black box. And so, and it'll happen in other contexts as well. What else is François saying here? Yeah, and so as we'll see in later slides, because of this restriction in the most developed version of machine learning today, it'll hit a wall. And there is no doubt that it'll do very well in these three realms. Now, if you've looked at Google Translate, it's improved significantly because of deep learning. If you look at speech and vision, and speech will make for speech-based computing much easier and much more practical. All of this is good, but you push it into other realms and say AI is going to take over the world? Hardly. Yes. So question is that when you have products like driverless cars and so on, will we hit the same kinds of issues that the SEC is bringing into the finance world? Absolutely. That's where it's stuck, actually. Let me tell you, I keep mentioning speech and image and language translation, but the other big success story in deep learning is, of course, autonomous driving. And it's the really big success story. And but do you think it's going to happen tomorrow, next year? The technology is there to have completely autonomous driving. Why do you think we are stuck where we are right now in terms of the government allowing us to do this?
Because it actually has to work.
So if I understand it right, you're saying that there are many questions that are not answered in the scenarios for autonomous driving, unlike in airlines regulation where you have all kinds of constraints that you have to meet. That it, or have I missed something? Oh, no, that's a statistical phenomenon. There are far, far more drivers than there are, than there are planes.
That's not a
Well, one might argue that if a billion people are driving at the same time, there are that many possibilities of human error. But if there are only 1 million flights being flown by highly trained people, there's going to be just a naturally low rate. But that's less of an issue, I think, than the ones that people are dealing with, and that's ethical issues, decisions to be made in impossible situations like.
Yes, actually, I do work. Actually, I study self-driving cars, and
You're not with Tesla, are you?
no, I'm not with Tesla. I'm a Udacity student, and the way technology is right now, it's there, but it's not quite there. You can think of your deep learning or classifier like if it actually provides correct answer like 99% of the time, that's pretty good. As far as self-driving cars, like they have to make driving decisions like 10 times per second. They have to be right every time. So like 99% of the time, that means that if 2 or 3 minutes down the line, the car is going to do something stupid, and that is just not good enough yet.
Okay, so what he's saying is that even though today's software for autonomous cars will do the right thing in 99.9% of the time in real life, there's still that 0.1% that is a factor. But that with a human driver, it's probably far higher number of times that percentage of the time that the mistakes will be made. But you're right, when it comes to a machine, then there's this insurance issues and so on. But there's also this ethical issue that of the kinds of decisions that we know about, but we don't know what the solution will be. So there's a school bus with 100 kids in it, and there is another bus that's taking octogenarians to Grand Canyon, okay? And they're about to crash. Now, given the speed, we know that only one of them are going to survive. What does the software choose? I think that comment is a nice kind of way of saying what I've been trying to say in different words. That is, he's saying that these deep learning applications are all very vertical. It works in one context and one context only, unless there's horizontal deep learning. You know what horizontal deep learning is? It's general intelligence. And we know that the current tools do not permit us to have general intelligence. We are zillions of years away from that. And even though people like DeepMind and Google will say that we are very close to general intelligence, absolutely not. So there is no way to bring in understanding into computer programming that we know of today, okay? And if neuroscience has some wisdom to give us, we don't know what it is yet. Anyway, so let's kind of put an end to that. Just leave it with the observation that in the case of autonomous driving, we are likely to have software driving cars resulting in far, far fewer accidents than human-driven cars, okay? And then these autonomous cars have tremendous other benefits of that they can impart, which you cannot today. They can, deliver goods to people who cannot move. There are all kinds of things. There are hospital-oriented things. There are children-oriented things. And the whole cost of transportation will come down significantly. So, yeah, all that is there. Yeah, and so the question is that humans make more errors. These systems are likely to make much fewer errors. How do you make a case for not commercializing this? It's stuck in this whole issue of situations we've never thought of. Okay, let's do this. When Big Blue of IBM defeated the chess champion, and when DeepMind created this AlphaGo thing, do you know what the differences are? Why did one succeed and the other succeed in very different ways? Anybody? So in chess, there are really only a finite number of moves. There might be zillions of them, but they're only finite numbers. So for a computer to do the permutation combination, it can do so. And it can then find fastest way to get to a move better than a human being can. But in AlphaGo, there are no finite number of moves. There can be infinite number of moves. And so the real stride made by DeepMind is significantly more. But they did it with something called reinforcement learning. And I'll come to that a little bit, but I don't want to get into too much detail of all of these things because that's not what this is about. Because the folks I'm trying to help out here, my customers in New York City and so on, they don't give a damn about all of this. They need to figure out how to make better business decisions, how to compete with others, how to beat the hell out of Google and Facebook and so on and so forth. So let's first get through that. Now, there are many other issues, okay? So I'm a trained econometrician, and I was lucky enough to do a part of my PhD under a gentleman called Larry Klein, who won the Nobel Prize while I was there. And he was one of the fathers of econometrics. And he used to say something that has stuck with me. He used to say that, look, you give me data, I can correlate anything with anything, okay? You give me a good computer, and those days the computers were called mini computers. We used to work on digital equipment computers with cards. And he said, you give me a computer, and he created this Wharton econometric model of the world, which had, I don't know, about 200,000 equations, which were simultaneous. So he had to invert matrices of very, very high order, and so on. And he would say that, look, I can correlate anything with anything. It has no meaning. You have to start with a hypothesis that first makes inductive sense, okay? Then you can, deductive sense. And then you can do induction from the data to see whether the two match. And that's called causality. Whereas in all of machine learning, in much of data mining and data science, beyond what is used in statistics, which is hypothesis testing, it's all about correlation. There's no issue about causality by and large. Now, let me define that a little bit. When you have a ton of data, which big data world has given us, you can argue that, look, we have all the data, so why do we need to have causality? We can see that this is related to that, and hence, if I push the line further, it'll give us a good prediction. And that's true. Or if you have enough data, but a lot of sensing of that data, continuous sensing, so you have a stream of data coming in, you can make the same argument. But causality still remains a problem, because if you look at some of these things here, let me try to, I can't even read it here, it's so small. Let's read it from here. So in machine learning, they don't really care about this because of this thing that we are predicting, we are not inferring anything. So there's a difference between prediction and there's a difference between inference. Business and economics needs inference. They don't need just a prediction. Professor Klein used to say another thing that was interesting about prediction. So he would say one of our big sponsors is Sears, which of course has gone down to nothing now. And Sears, the CEO would attend all the meetings, and he would sleep through most of the math, and then he would come out and say, what's the prediction for GDP for so-and-so countries and the United States? And so Klein would ask him, why do you come every year and pay us so much money for this? Yeah, very, very simple. Your forecast of the GDP, we are 2.5% of the GDP, so we know what our sales are going to be. And so, you've heard of these causality issues. More police in precincts with higher crime, does that mean that police cause the crime? Okay, and so on. So these things can be disproven by what are called counterfactuals. And there's a guy called Judea Pearl, a Turing fellow in UCLA, who has done enormous work on this counterfactual thing. And so if you persevere and do tons and tons of work, you can equate a correlation to causality, but it's tough as hell to do. So counterfactuals are you take what you have as your prediction and the chain of reasoning, and you say, okay, what if the chain of reasoning is opposite? What if there are other variables affecting this reasoning, blah, blah, blah. So you can dream up a whole bunch of counterfactuals and then test those, and then get causality. It's a tough job. So what this graph basically says is that with decision trees gives you the biggest causality, obviously. It's one of the easiest tools and one of the best used tools. Even regression and all that will give you, Markov models, random forests, they're still okay. The moment you go up to machine learning and neural nets, you're in the world of, zero explainability. And that's not good for business. So what's the solution? So we are now coming to a few solutions. One solution is to bring in probability and uncertainty into machine learning. And there's a whole stream of thinking on Bayesian. And so Bayesian statistics has been around since 1772 or something. So it has built up a whole wealth of great minds, output of great minds, and that's tremendous. So Bayesian statistics is a very well developed. So you can bring in Bayesian statistics by saying that the observations we have in our database, this picture of a cat, is not really the picture of a cat, it might be. Okay, so let's say that it's a mean of the distribution. So typically you put in Gaussian distributions, and then you're able to create statistical features to this data and be able to get better causality. And so these Bayesian models are getting to be more and more popular. If you look at the number of PhDs happening today in machine learning, particularly from England and Canada, they all have a lot of this Bayesian input in them. So I don't want to get into too much detail here. It's kind of esoteric topic. If we are able to do this Bayesian version, and I've used it with customers, it's actually easier to do. And the problem being they're not very scalable. And the reason they're not scalable is once you use things like Brownian motion, you need cubic power permutations, you need heavy parallel processing. It becomes a real issue. It explodes. But with small data, with relatively small data in a business setting, it gives you much better insight. For example, one of the things we did when I was in McKinsey, and we now do it quite a lot in this world of valuation, is that discounted cash flow is not necessarily the best way of looking at the future value, right? Because if you look at decision trees, they actually cover the whole gamut of possibilities, right? But really, in reality, every time you go through the decision tree, you get more information and you make the better decisions. So the whole traversal through the decision tree is kind of an optimal path. Whereas the discounted cash flow will give equal weight to all of the paths and then give you an average. So it will always miscalculate. So let's say that curve over there is the projection of some measure of value. But in reality, you'll have some points that are above, points that are below. Now, if you're able to somehow figure out that when you're here and you're able to figure out that it's going up, and you start going up with it, and then when it goes down, after it goes down for a while, you figured out what it is, then you're able to ride that. So you're going to make good decisions on both sides. If it was a stock price, you would buy call options on the blue side and buy put options on the red side. I don't know if that means anything to many of you here. But the fact is that you can profit from upside and downside. And that's what corporate strategy can be interpreted to be, that when we see opportunity, we invest in it. When we see recessions coming or a lack of demand, then we desist from investing. So we have a choice. We have a choice to make more investment, and we have a choice to make less investment. And that's strategy. And when you, for example, if you're in the mining business and the oil price is going like that, or metal price is going like that, you will try to keep your oil in the ground or your minerals in the ground when the prices are low and start digging them when the prices are high. Okay, or let's take another example. You've got a assembly plant in Japan, one in the US, and one in Germany. All right, and so you have three currency regimes. All right, if you're able to switch one off and switch one on very quickly, you will try to follow longer-term currency movements and get the most out of it. And this is the kind of thing that businesses do. So to be able to do this, you need to have a probabilistic machine learning concept, and Bayesian provides you with one such. It looks like I'm putting a lot of people to sleep. The final piece I have here is game theory. How many people have heard of it or worked with game theory? Oh, great, so that's quite a few. Now, game theory is a stock and trade of a lot of pricing decisions that are made by today's corporations. As you know, post-Reagan, we've consolidated the industrial world to the point that there are only a handful of players in each of the business sectors. So they're called oligopolies. In the Silicon Valley area, we've created, once again, monopolies, which didn't exist before, but Google is a monopoly. Facebook is a monopoly, Amazon is a monopoly. And they do their pricing not using standard, or random things. They do their pricing based on what the others will react to their pricing changes. And so if you look at Amazon pricing, if you really persevere, you take a high-priced item and you track its price. Okay, don't buy it, track its price. You'll see the price is changing quite a bit. Okay, and that's called dynamic pricing. So what they're doing is they're looking at demand-supply curves all the way around, and they're looking at everybody else's pricing out there, and they're coming to decisions on a dynamic basis. So this is a very important thing in today's world of business. How do we get this into machine learning? And lo and behold, there is a thing called adversarial learning. Have people heard about it? So adversarial learning is when you have agents play with the data and play against each other with a reward function, which is also, one version of it is reinforcement learning, but this is adversarial. And it was used partly with the AlphaGo thing. But the idea here is that you don't give them any inkling of what to do. There is no loss function to be assigned. They create the data, the agents create their own loss function. Okay, and they're able to make moves that seem to be as good as game theory and even come to Nash equilibrium situations. And that's very exciting, because in game theory, in reality, it's a world of certainty. You put some payoffs of every action, and then you try to make decisions. But in this situation, you can have a dynamic situation where the payoffs will be given by the algorithm itself. Final slide. The dream of any enterprise today is to create what BCG has called the strategy machine. And the one that's closest to it is Amazon. And although I don't have a lot of insight into exactly what they're doing, but I've put pieces together from people consulting with it. And they have this amazing man-machine system with enormous data that that have the whole supply chain in it, all the demand patterns, what's happening in the currency zones, what's happening with price elasticity, what's happening with other people's moves, et cetera. And so they can, with the data coming in automatically, they can make decisions. And then they can change things also and try out different kinds of strategies by an intervention. So it's not only all AI, but it's hugely AI. So that's kind of the pipe dream of all machine learning experts in the enterprise world. So recap, let's train more data analysts using data wrangling and visualization tools in real-life business context. That value derived by enterprise is so large that there is room for millions of such people to be employed. Now, somebody asked about, is it a low price, low cost, low wage job? New York City, these guys, Udacity has started this Saturday-only training for a year for data analysts, and you do this while you're working somewhere else. Starting salaries have been $85,000. In other places, similar. So they're not bad at all. And not all of us are math geniuses and computer geniuses. Many of us might make that a career, and then you can rise from there. And so I think that's one of the best things that can happen to people who are, not going to be mathematically oriented or machine learning oriented. It's a great service also to enterprise. If you are going the whole hog, arm yourselves with the best tools available, some of which I talked about, but be always aware of the fact of the limitations. Don't try to overpromise or overdo things that will result in very brittle solutions. Let's all be principally data-driven. We still believe that data should drive decisions, but work within the constraints of well-known business models. If you're working in if you're advising an oligopoly and doing AI and data-driven decisions there, you have to be aware of the game theoretic aspects there. If you're with a mining company or a global assembly company or whatever, then you have to be aware of the foreign exchange regimes where they have the optionality and so on. That's about my story. There's a little blurb on shareholder value. This is the book I talked about that we created in McKinsey. And lo and behold, I found recently that The Economist wrote up a piece on it asking what is the most important business and economics book of the decade. Is it Piketty's Capital? How many people have read Piketty's Capital or have heard of it? Wow, there's at least 2 hands or 3. No, lo and behold, it's the McKinsey book on valuation. So with that plug. And one more shameless plug. This AI Labs thing that you're seeing at the bottom is a new venture I've had funded. And it's going to have this blended learning training centers in 18 tech hubs of the world. We're starting January next year, we're starting 5 in India and 1 in Palo Alto. And then we are going to do other parts in Asia, 1 in East Europe, and so on. So the idea is that wherever there's technical talent that needs to be trained correctly in the whole series of things from data wrangling to machine learning to deep learning to enterprise platforms, we're doing that on an annual program, which is for working people. And then in the Palo Alto Center, fresh students or other younger people can do a second year and get themselves an MS in computer science or an MBA in AI.